Okay. Okay, then let's start. Yeah. I remember we already discussed quite a lot of this first version of our binary search tree. This first version, it's just a linked way implementation, okay? And let's just do a quick review, okay? The bin node, as usual, nothing new, that it's linked way implementation. And for this version of binary search tree, we only have one instance variable, okay, the root node. And then we discuss the search method, insert method, we already know of this, and the search tool serves as a utility function for the delete method, okay, so remember that. And we also discuss delete method. And the in order, pre-order, and the post order, etc., all of those recursive call we also learned. And I remember, oh yeah, and I remember last class, we also discussed the print level order, that we use a queue, and then you can level by level output your tree, but still it's not a fully version of the tree view like, okay, but that's getting close, is it? So today, let's take a look at this one about the tree printout. How about let me do this first. I need to admit the student. And first, let me run this, okay, so that you
What?
can.
Tell him you're pooping.
Someone, can you turn off your audio? Hold on. I think I need to stop sharing. How do I mute? Okay, I need to get back to the sharing. Okay. Okay, so for our tree, so here is what we are going to see the coding. Okay, so the tree output, and it's kind of vertical. Okay, and it's so the left part. This is the left part. So we have 55. Then we have 40. I believe 38, 39, 42. 42 is, oh, I forgot the, so 30, oh, 42 is here. Yeah, that's 42. Is it? So that's the left of the root. So this is our root. Hold on, I need to get to the student. But you see, we are going to output it like this, is it? And then we have 70 and following on. Okay, and we are going to output the tree something like this. So how do we achieve this? Let's go back to the coding. Where is my coding part? Okay. So let's take a look here, okay? So we call it traverse pre-order, okay? And so first we are going to start at the root node, is it? And if root node is empty and you don't have anything, and this method itself going to return a string. So what you just saw that something looks like this, is it? And then it's something is like this. And basically what we will see, the both of this function, what it does, it's kind of to build a long string. Build a long string, okay, and the formatting with individual line, okay, represent individual branch. And then you print out this long string. Okay, so that's why the return type is string. Okay, string. So, and previously in CS2 you learned that, and with string it's too much waste of memory. So that's why we use a string builder, because we are going to keep concatenate each branch. So we use a string builder, and we first start at root. So that's why you get the root data to this string builder. And then did you see we are going to return this string builder as a string. Okay. And for this way, what we are going to do is, and let's also get back to take a look at the running result. And just take a kind of look. And so there are different signs here. We have this kind of T sign, and we also have a vertical line and some space, and we also just have this L line, So there are different, and then this is the data part for each individual node, okay? So you kind of keep expanding this, and each time, you see, for each level of node, it's going to be in a new line, okay? But in a new line, you also need to align where, so that it knows if it is a child node of the previous node, So that's why over here we use formatted to define the level so that it can be indented, okay? And then let's get back to the tree again. Okay, so that's why over here we have these two string defined, pointer right. Did you see? It's just an L kind of, And the pointer left. When you do pointer left, you need to check if the right part, the matching pair right part, if it's null or not. If it's not a null, then you use the T. Otherwise, you just use the L. Okay, and then if you take a look here, we call another method called traverse nodes. Okay, call this to kind of utility method, traverse nodes. Okay, and if we take a look at the traverse nodes, let's take a look. So this SB is that long string, long string for tree output. So that's and anyway, so later on we will see this part is padding. At this point from root, we don't have any padding. Okay, later on we are going to define this padding. And then we need to pass. The third one is a string. And the string will let you determine if it's a L or if it's a T. Okay, so that's the third one. And the fourth one is a node. The fourth one is a node. And the last one is what? Is a Boolean. That's the last one. Okay, Boolean. Okay, so that's, and what over here, if you take a look, and it call this method twice, because it's started at root. Start at root, then we have 38, and 70, So you go with left, and then you go with right. So we need to take care of both. That's why we call both of these two methods. Okay, then let's take a look. So what this traverse node it did is, first you need to make sure that node is not null. If the node is null, you are going to move to the new line. So it's a new level. So that's why you add this /n. And you are also going to add the padding. Is it the padding? So because you need to know, like the padding is, so how many you need to indent it. Is it something like this? Okay, so that's a padding. And also append the pointer. Pointer is either the T or the L, is it? And following the data, is it? So if it is this case, it's going to be 35 something, is it? So anyway, so these parts take care of all of this, okay? And then we need to deal with the padding, is it? Because padding determines the level, okay? So padding kind of matching the level here, is it? So this if you have another level, is it? So that's what the padding does. So if you take a look, did you see? So it depends, is it? The padding, so it's a string builder, it's based on whatever passed in. So it's going to also concatenate. And then if it has the right sibling, so that means if it has the right subtree, is it? If it has the right subtree, then you need to do the padding with a vertical line. If it doesn't have right part, then you just have the space. And also we align the space well, okay, so that we can do the indentation well. Okay, so that's regarding padding part. And then the same thing, is that you need to decide if it's the left subtree or the or right subtree or left subtree part, is it? And after that, did you see it recursively? So this method, traverse nodes, is a recursive method. So that it's kind of like our in-order, pre-order, those method, is it? But here its purpose is using this traversing to build, using this recursive way to build what? To build that long string. Because finally you just get that single string and then it's going to print line by line, is it? And after that, did you see, we just call this method print. The print will have a string builder, is it? And what it does is it's called that traverse pre-order, is it? Call that traverse pre-order. And then it's going to output whatever it has, okay? Okay, so this is regarding the simplest. Okay, so this is just some extra information, okay, for print of binary tree. There are multiple ways, a lot of ways to do the print. And for the horizontal, like the real tree-like one, our textbook, I believe, had an example, but that one has a limitation as the tree can only be certain wide and certain deep, is it? And not like as flexible as this one, it can go kind of quite, apply for a quite large tree, okay, horizontal, it's, you need to plan. So it's, I haven't investigate really deep to find how to flexible print out the really horizontal spread out tree, okay? And if you are interested, maybe you can find out. Okay, so that's regarding this simplest version of binary search tree, okay? What today we will discuss is, if you recall, for linked list, that we also discussed the linked list regarding iterator. Iterator way, is it? And so for binary search way, can we also provide some way to do iteration? Is it with iterator? Is it? And in order for that to happen, so that you can also support, if you recall, the for each loop. If you use my version, that binary, if you use this linked way, you cannot use for each loop. Is it because the iterable not implemented, is that you cannot do that, okay? So over here, the next implementation, we try to also support for each loop, okay? So then let's see the iterator issue, okay? So over here, we try also follow the collection, okay, Java collection. If you recall, Java collection is an interface. That if you recall, iterable is the very top level of interface. Is it? Then we have collection interface. Is it? And we also learned, if you recall, a list interface. Is it? We also learned queue. Queue is also interface. Is it? And I remember and there are some other abstract class, is it? And then we learned under this, the linked list. The linked list, it has the feature from both list interface and queue interface, if you recall, is it? And from list, we also have array list, is it? And it's from queue or from deck, I don't remember. It's from list, I believe, yeah. And through some list or vector, I don't remember exactly, you can help me double check, okay. So anyway, we also learn stack. And the stack is, so all of those, array list, linked list, stack, they are concrete class. Concrete class. And in Java, we don't have specific like the queue concrete class. We use a linked list to represent queue. That's what we learn. And this semester, we will learn more, okay, regarding the collection, okay, collection. But anyway, collection is the interface. Okay, iterable is also an interface. Okay, and this list queue also interface. Okay, and really those are concrete class, okay. And then, so what over here in collection, we try to here first to define an interface, we call it tree. So it's an interface, okay, here, be careful. And we say we want to extend collection. So we want to borrow a lot of features supported by collection interface. So that's why we say we extend the collection interface. So the tree is a sub interface of collection interface. And then over here, we add some abstract method. So it's a search an item in a tree. Is it a binary? Insert an item in a binary search tree. Delete an item in a binary search tree. And record the total number of items in a binary search tree, okay? So here it's not in a binary, it's just the tree interface. And over here, and temporarily over here, we just leave them empty, is it? But we define them as default method for in order, post order, and pre-order, okay? So they are default method here. And if you record interface, I'm not sure for interface. And interface can take just a quick review, okay? Abstract method. And who remembers, so here default method. What's the third type of method? It also take static method. And both static and default, they are implemented inside the interface. Okay, and abstract method leave it to be implemented by whatever the class going to implement the interface. Okay, so that's the general idea. And for default method, whenever you upgrade your interface to a new version, you can always add default method. That's the purpose of default method. Okay. Okay, and then here, if you take a look, like is empty is also default method, is it? It just call what? It just call the abstract method. That's fine, is it? And also, if you take a look, the contains method, it's also default. It just call what? So call the method, abstract method. So call abstract method defined inside the interface. Interface itself, is it? That's what it does here, is it? And basically the search hasn't been implemented, is it? But it doesn't matter because whatever class implement, they are going to implement. So basically the contain method, the default method completely depends on whatever the class implements it, is it? Okay, and the add method, same thing to call. It's a default method, okay? And you call the insert. And the remove is also a default method, and you call the delete, is it? Method, abstract. And here the size. Oh, size is a default method, and it call what? The get size. Get size is abstract method. And then you provide the size method. And then over here, we call the empty is also there to call this the size method default. Okay, so here just kind of interesting, multiple levels. And the contain all, is it similar? Is it? And we didn't implement. You can try to implement and add all. We also didn't implement. Okay, but we not to implement, but you still needed to like do something like return true or false to fulfill, assuming it's implemented, okay? Because it's already defined as default. So that's why here we provide as return either true or false. And remove or return or and to array, is it? So it's as usual, is it? Similar as what we saw for the collection interface is basically it's try to cover all of the collection methods, okay, and plus a little bit of it itself. So we define this tree interface. And then next, let's take a look. This binary search tree that we defined. Okay, so for this binary search tree, then I said I'm going to let it implement the interface that is just defined. And if you compare this one with what our previous version, the previous version, it implements what? The comparable interface. You need to do that. Is it because binary search tree is based on comparison? Is it? So you need to anyway somewhere provide the comparison, supporting comparison. But here, if you say, oh, this one we didn't provide, how are we going to implement the comparison? Is it? So this example shows a different way. And let's take a look. Okay, so what it has one instance variable called root. So similar, okay, and the type is tree node. And we will see tree node is similar as a binary tree node, okay. It also has a method called size. So it keep tracking of how many nodes in the tree. And if you take a look, there is a third instance variable. So this is instance variable. And it's all defined them as protected in this example. Okay, this it didn't provide them as private. And this is not recommended or not recommended, okay? Because in our case, just this example just to try to explain the iterator consideration inside the tree, how we deal with it. We didn't worry about security, software design, those aspects, okay? So that's why over here, and it's for the convenience of explanation, we just define them as protected, okay? So if you take a look at this instance variable, what's the type? The type is a comparator interface. If you recall previous, we also discussed comparator interface. Is it comparable? Comparable, it supports kind of nature ordering, is it? And the comparator, it's more, it provides more way to apply comparison, is it? So that's why over here we use comparator. And if you take a close look of collection, Java collection framework, you will see a lot of, for collection, package, a lot of method, they take argument, the parameter type also as a comparator, okay? And that's the reason, okay? But anyway, so here we use a comparator as our instance variable. Okay, if we use comparator as our instance variable, etc. So then over here, so this is our binary search tree, is it? So for this binary empty, going to create an empty one. This as a default one with a nature order comparator, is it? So what it does is try to initiate this instance variable to something like this. So anyway, hold on, okay. So anyway, so it says, okay, if you want to compare two items, is it, then both of these two items, then it's going to call the compare to method from the comparable interface, is it, to achieve the goal. So it's going to call the compare to method. And so here, let me ask you a question. How about this is going to be our first quiz question. So this is an interface, basically the type. Is it? And oh, yeah, true. Here, what is this? Is this an interface? Something, or what is this part? Anyone still remembers?
It's like E1, E2 arguments for the function, and then we call compare to method to compare them.
Mm-hmm.
That's a lambda expression, isn't it?
Yeah, this is very good, lambda expression. What it's going to generate. Because whenever you do, just remember, okay, in programming language, whenever you do assignment, it's either primitive type, assignment, or reference type assignment. And here, definitely, it's not a primitive type assignment. Is it primitive type assignment should be integer I equals 10. Is it? And all this happens on what? On stack memory. And here definitely should be reference type assignment. And if it is a reference type assignment, what should be on the right? What should be on the left? So what's on the right? This right, what it is?
An object of an anonymous class, and this class implement comparator interface, implement the compare method that define in comparator interface.
Yes, yes, very good. Okay, if you recall lambda expression, basically it's kind of a shorthand for anonymous inner class. Is it? And what is anonymous inner class? Just use once. Is it? And basically it equals to new something. Is it? So some class that's implements who? Comparator. Interface. Is it? So that's why over here basically to create an object. That object type, we don't care. It's some anonymous type. But no matter what, that type must implement the comparator interface. Is it? Okay, then here is another question. And we know interface cannot be used to create objects. Is it? But why here you assign an object to an interface type of variable? The type also doesn't match, looks like. The right side, it's new some type. So maybe some class. Is it? And the left side is a comparator. Why we can do this? Still remember the keyword? It's in OOP.
Dynamic binding.
Yes, okay, so this is dynamic binding, is it? So that's the concept, okay. So anyway, so the quiz question, you just said, this is a lambda expression, is it? So it's going to create an object that's implemented the comparator interface. Okay, so that's the answer. That's why you can do this assignment, okay? And because the right side, it's some object. That object will implement the comparator interface. Because anyway, it's implement comparator interface, so that's why you can assign it to some variable. Is it? The variable type is also comparator. Okay, so that's fine. We need to be very careful, okay? And then if you take a look at this one, the second constructor, it's the same, similar, is it? But this time, your comparator, you already defined. So you're going to plug in with some comparator, argument. Is it argument? And then you're going to assign it to this instance variable. Is it instant variable? Then here is another question. How about this is second quiz question? Question. So anyway, so this is the constructor's signature prototype. Is it? So when I call, so when I create a binary search tree, how do I plug in the argument? The argument. I should plug in what? Is there some way you can just define a comparator object? You cannot, is it? So you cannot plug in a comparator object. Is it because a comparator is an interface? So in this case, the second piece question answer, when you plug in, you still need to plug in some object. That object's type implemented comparator interface. Okay, then that works. Okay, so be careful. So you can also use, you can also define some, use a lambda expression, is it, to create an object and pass in, is it? So that also works. Okay, and then let's take a look. So here we have multiple constructors. The third constructor, it's going to build the binary search tree with an array of items. Okay, and the same thing, the first thing, I'm going to initiate the comparator instance variable, is it? I define it some way, okay? And then you are going to just loop through the array and call add method, okay? And the add method is from where? Is defined in that tree interface, okay? Be careful here. And then next, let's take a look at search. And the search, if you take a close look, it's not a lot of news. We always start at root node, is it? And then because here we don't use comparable interface, we use comparator interface, is it? So that's why you can directly call c.compare, is it? And then you compare with what? So this is whatever the item you want to search. And the current is going to be your cursor, is it? When you do the search, your current node. So you're going to compare. So that's why you call the compare method. So over here is we call the compare method from comparator interface. Be careful, okay, in comparable interface. Compare, it's what? It's the compare to method. The method name is called compare to, okay? And the comparator interface, why you can do this lambda expression is because comparator interface is what? Is a functional interface. Okay, keep that in mind. If it's not, you cannot write lambda. Okay, and you cannot write a lambda expression for the tree interface. You cannot do that. Okay, and because the comparator is special, so that's why we can do a lambda expression. Okay. Okay, so anyway, so then we call add. Okay, so the search, is it? So here you call, so here we make use of that instance variable C. Is the same thing? C, is it? And else, is it? So we just keep doing, is it? Anyway, so this is search, use the while loop. Okay, use while loop. And then do insert. Is it? Do insert. And for insert, it does what? Insert. So insert, of course, you first need to create the new node. If it's a root node, then you just add it. Is it? Otherwise, still the same thing you call comparison. You need to determine it's going to move right or move left. Is it? So we also have a parent node to keep track. Is it? So anyway, so you find the place, then you are going to insert. Is it? So we implement this insert method. okay. Insert method, so anyway, after you find the location, you're going to create a new node, okay? And here it also called create a new node. And at the same time, you also increment the size. How about let's go back to take a look at the tree. I don't remember the insert. Oh, yeah. So if you take a look, if you remember the tree interface, the insert method in tree interface is an abstract method. Is it an abstract method? That's why over here, if you take a look, okay, here, yeah. So for search, we have that override. That override is from who? It's that tree interface. So the abstract method. Okay, that's where this override happens. So the search method is defined as abstract method in that tree interface. Okay. So similar for insert. Okay, for insert, it's override. Is it? And over here, in order, and we haven't done the, oh yeah, the insert, same thing. That's where this override occurs. It's because of the tree interface. We define that abstract method, okay. So anyway, the remaining logic is similar as my version of the implementation of the binary search tree, okay. And then in order, okay, in order it's similar as what we discussed, post order, similar, pre-order, similar. Okay, then let's take a look at the tree node. It's also pretty similar as what we previously defined. It has a data part and the left and the right tree, etc. And the get size method, we also override, etc. And here we also provide a public method for get root, is it? And this is just trying to demonstrate idea, okay? In the real world, when you design a data structure, you don't want to expose the instance variable, okay? So you need to have some way to protect it, okay? So here just try to show some idea. Okay, next let's see. So for this class, we add another method we call pass. So we want to find the item, and we also want to know the whole path get to the item. Okay, so like 55, then we have that 38, there's 39, and 40 something, is it? And here is 35, suppose. Okay, suppose here is so there is no good items here. So anyway, assuming you want to search 40, this item, that so E is 40. Then you're going to start at 55 and move to 38. Then you move to 39. Then you find 40, etc. So I wanted to know this path. How do I keep track of each individual node and following that order to reach this node, etc.? So that's what this method does. And it return what? Return an array list. Okay, array list type is what? It's a tree node. Okay, tree node. So we first need to create an array list. Okay, we start at root. That's it. And then we use the while loop until we find the item. Once again here, you call the compare method. As if from the comparator instance variable. And here, so each time when you get to the new node, you add the node to the array list. That's it. And then you return the array list. Then in this case, you get the whole path, reach to the item you want to find, okay? So this is later on when we learn some other complicated tree data structure, we will see this concept also used quite often, okay? So to keep track of paths, okay, and also graph. Okay, for delete, same thing, as we override because the tree interface, and similar as what we discussed previously, okay, not a lot of new thing. Okay, the major concept here is about the iterator. Is it about iterator? So we want to provide the method for the iterator, and it returns an iterator. Is it? And what over here we are going to do is you're going to return something. Is it? Return some type of iterator. Is it? And if you recall for linked list, when we discuss the iterator, it's similar. Is it? So you need to define some class, and that class going to implement iterator. Is it? Iterator is also an interface. Interface, is it? And this iterator method comes from where? So who still remember? That iterator method.
Does it come from collections?
Yeah, we can see it's from collection. That is definitely right. Because what? Because the iterable interface and the collection. Is it? It's because of the iterable interface. And that's the method. Is it? And if you recall that for each loop, any data structure, if you want the data structure to be able to be supported for each loop, you must implement this method. Is it? Iterator method. Then inherently it will support iteration. Is it? Using for each loop. Okay, so that's the whole logic here. So anyway, so because this iterator method, the return type is an iterator. Is it? So that's why over here we define the class. That the class implements the iterator interface, okay? Because it's completely kind of idea here, okay? And for this class purpose is to serve for iteration. And for iteration in binary search tree, so iteration, anyway, so here it's do traversing. Is it? For binary search tree, when you want to do traversing, you need to follow either pre-order or in order or post-order. Is it? So that's why over here we said, okay, for our iteration, we want it to do in order iteration. Okay, we are going to go this route in order, okay? And what this class has, it has an array list, okay? And we also has some count to keep track of where you are currently at, okay, when you do the traversing, is it? And this is the constructor. So this constructor call another method in order, is it? And the in order is defined here. Okay, that's the in order method. And the in order does what? It call another method in order, is it? This is also in order method, is it? And it takes a tree node, is it? And these two methods has the same name, but different signature. What do we call this? Who still remember the name for method? It's over what? We learn override. There's another, it's easy to get confused for beginner programmer is override and over what?
Overloading.
Yes, very good. Overloaded. Is it? So overloading here. Okay, these two methods are overloaded method. They have the same name but different signature. Overloading and overriding, two different concepts. Okay, overriding is between superclass, subclass, the same method or interface. Is it? So that's and overloading, it can be in the same class and you have multiple same name method, but they must have different signature. Okay, so be careful about this, be clear about this concept. Anyway, so it call this in order, pass in with the root node. Is it root node? And the root node, so if it's null, then of course you don't need to do anything more. Is it? Otherwise, it's in order traversing. Is it? In order traversing here, we are not going to just do traversing. What we want is to keep track of the array list. So we have that array list. This array list used to keep track of in order nodes. Is it? That's what it, oh, here, sorry. That's what it goes here. Okay, in order nodes, okay. Okay, and then, and here it says override. This override, so has next, you remember for iterator, interface. So whenever you implement an iterator interface, you must override has next, and remove. You must implement the three methods. Is it? Iterable interface just has a single method called iterator method. Okay, iterator interface has this three methods. So you must implement all three of them. Okay. Okay, so let's see then. So for this tree, how do we keep track of where it is? It's different to the concept from the linked list. Is it? So that's why we use that current. So based on the index, is it? It's an array list. So you use the index. So where is the current? So current represent your current traversing node. You use it. Basically, it's kind of you convert a binary search tree to an array list, store it in an array list so that you can keep track of where I'm at right now. Okay. So, okay, so if the current is not to reach the end, of course, it still has next, otherwise false. That makes sense, is it? And how do you get the next item? Of course, you can array list, you can call array list get method and use the index to retrieve it, is it? So this is easy to understand. And then for the remove, we need to be very careful, is it? And if it's already empty, then you have nothing to remove, is it? So that's why you throw exception. Otherwise, you can just call delete and you specify that node, because what this returns a node. Then you call the delete method to delete that node, is it? And you delete the node, you need to clear the array list. And then you need to do re-in order again. Okay, so be careful this two steps, because in binary search tree, whenever you delete something, the tree needed to be rearranged, is it? That's why over here, you need to kind of, the tree rearranged so the in order the order also changed, is it? So that's why over here, you need to call that in order again. You need to call this in order again so that it will start to create that array list also again. Okay, so be careful. So if you compare binary search trees iterator, it's much more complicated versus linked list version. Okay, so hopefully I get all of the points clear here. Okay, this method clear is pretty simple. Okay, that's binary search trees. Okay. Okay, we get this one clear. And then next, let's take a look the driver part. Okay, so this time we create the binary search tree, pretty straightforward. You just insert of the item, is it? And then you can do in order, pre-order, post-order, is it? You traverse all of them, is it? And you can also search a certain item, is it? And you can get a pass. Okay, you can get a pass. And for the pass, then what you do is you output each individual item along the path. Okay, let's take a look at the running result to see what it looks like. So we have Adam, Daniel is off this. So the path is that from root to Peter is that through this. This is in the tree, okay, in the tree. And then let's take a look here. A path from root to Peter, is it? So that's, it can give you the path, how to reach specific item. Okay, that's what this part means. And then it also, the next part shows is a number binary search tree, okay? And then you can also do in order, pre-order, post-order, is it? Let's see, the order, yeah. So it's also have that in order search for the item. And then next, let's see what it does. Oh, then here, if you take a look over here, is it? Here we use for each loop to loop through the tree. Is it? That name tree. Name tree. Is it? And why you can do it? It's because that iterator method already implemented. Is it? Iterator method implement, that means you already complete the implementation of iterable interface. Is it? Even though our tree, this tree interface is defined, implements connection. Is it collection interface? But a collection interface is what? It's a sub interface. So here is iterable and it's collection. Is it? So inherently, you basically also implement iterable interface. Okay, and you implement this method, so that's why inherently, implicitly, you can go ahead to use this for each loop. Otherwise, you cannot, okay? So be very careful why we can do this. And then you can also do delete, so nothing new, and we can print a tree, okay? So nothing new here. The print tree is pretty straightforward, just use in order, post order, and pre-order to output the tree, okay? Okay, that's this example, the iterative way. We also complete the implementation, okay, the discussion. And one more topic in binary search tree we will be able to finish next week is about the Hoffman coding. Okay, we will see binary search tree binary tree used in the in compression in some other technique. Okay, so anyway, so that's all for today's material. Okay, so